All right, so this video is going to be on the two mechanisms for nucleophilic substitution specifically, but we're just going to introduce them both and then kind of go over one of them in a little bit more detail. So here's one. Let's say we had this like primary alkyl halide with a nucleophile. We get this substitution product, and the same thing for this tertiary alkyl halide, right? Highlight those in blue just to kind of accentuate those, as well as highlight those nucleophiles in red just so you can follow the substitution pattern. Okay, so on the top reaction, we might have a scenario where the rate is equal to K times the alkyl halide times the nucleophile, the concentration of each of those, right? Where we could also have a scenario where the rate is equal to K times only the alkyl halide. And these are essentially the two different types of substitution reactions. We have a second order on the top and a first order on the bottom. And that kind of gives us some insight as to what the mechanism might be. Okay, so for example, let's say we have this methyl bromide, and then we have acetate. Again, the leaving group, bromine, is highlighted in blue and the nucleophile highlighted in red, just to follow that a little bit easier. This particular one is second order. So that means that the rate is equal to K times the concentration of the bromomethane or methyl bromide, whatever. Either way, we can call it that. And then we have the concentration of the acetate as well. So I wrote it in two different ways, so that way you can see the two different forms that you might have it, see it written. So the CH3COO minus or the CO2 minus. Okay. Here's another scenario where we have real nucleophiles and real leaving groups in this case. So this alkyl bromide right here, and we have the acetate again, okay? So I'm telling you that this particular reaction is actually first order, okay? And the rate is equal to K times the concentration of the alkyl bromide. Okay, so why would that be when we have the same nucleophile and pretty much the same leaving group? So why is there a difference? Well, we have two different mechanisms, okay? So there's basically a one-step versus a two-step process. Now that we can categorize these as an Sn2 mechanism, which is substitution nucleophilic, SN, and then bimolecular is what the 2 stands for. Okay, so what this means is that the rate is equal to K times the concentration of the alkyl halide, or the electrophile times the nucleophile concentration. Okay, there's also the Sn1 mechanism, which is substitution nucleophilic unimolecular. That's what the 1 stands for. Now, the rate is equal to K times the concentration of the alkyl halide only, or essentially the electrophile. So this Sn2 mechanism, that corresponds to this top reaction right here, okay? Because the rate was dependent on both the alkyl halide as well as the nucleophile, and it was second order, okay? So here's the mechanism. We have the nucleophile attack, and then the bromide leaves, and that gives us our product, and we get bromide as a kind of a byproduct on the other side, right? So let's talk a little bit more about Sn2 mechanism. So this is called also a concerted mechanism or a concerted reaction because we are making and breaking the bonds in one step. It's all happening at once or in concert. And here's our energy diagram. We got the reaction coordinate again on the bottom. And this would be for an exothermic reaction. We have methyl bromide getting converted to this compound on the bottom right. And then we also have our acetate as our nucleophile attacking, right? I'm going to actually change this to a dotted line because it's basically going to help us kind of envision the transition state, which I'm drawing here on the top. So the acetate is kind of attacking that carbon, right? And so we got that carbon in the middle of both the nucleophile and the leaving group. Got delta negative charges on both of those, and red dotted lines indicating the partial bond formation as well as partial bond cleavage. Okay, so that is the transition state. And it's basically it's kind of a picture of showing you how it's a concerted mechanism. Okay, so here's also our activation energy as well as our enthalpy for this particular reaction. Okay, well, so the next question or topic we need to raise is, how does the nucleophile approach the electrophile? So basically you can approach from two sides, right? So we can approach from the front or the back side. Okay, and now this would mean like the coming from like behind where the leaving group is, or right on the same side as the leaving group, right? So the nucleophile here or here. Let's say well, let's highlight this in red first, because I like to show the nucleophile in red because that's the electron-rich species. And then attacking from the left or the right, that's the left is a backside attack. So it's basically approaching from like kind of like quote unquote behind the leaving group. And then the front side attack is basically approaching from in front of the leaving group. Okay, so and that's because when a leaving group comes off, it's going to go to the right, essentially, if you break off that bond. And now these two possibilities were a thought, right? But Walden is the man, and he figured it out for us back in like the late 19th century. If only I were like 100 and some odd extra years old, right? So we've got this compound right here. What I'm going to do is kind of just draw out a bunch of kind of sequential reactions, and they're going to help us explain why we know the approach of the nucleophile for Sn2 reactions, okay? So let's see. Right there on the left we have malic acid, and remember that negative sign indicates the levorotatory malic acid, so that's 1 enantiomer. And then on the right we have the positive, so dextrorotatory chlorosuccinic acid. That's after the addition of PCl5. Okay, so the only important thing we need to know is that we have OH going to a Cl for that change in groups on that carbon. After the addition of silver oxide and water, we get that OH back. But notice that the malic acid that's formed is the dextrorotatory enantiomer. Okay, so that's exactly opposite of the original compound. Okay, now after the addition of PCl5 and ether again, what we get is that chlorosuccinic acid, and it's the opposite enantiomer again. It's the levorotatory this time. And then what do you think we're going to do? We got to add that silver oxide and water to get the negative, or the levorotatory malic acid. Now what we gather from this reaction is that throughout the sequence we go from one enantiomer to another. So there was an inversion about a stereocenter at some point. But we don't know if it's between malic acid and chlorosuccinic acid, or from chlorosuccinic acid to the other malic acid. Which reaction did the inversion? Well, that required further studies. However, we do know that there is an inversion nevertheless. And the way that this happens is via a backside attack. Okay, because that basically forces everything on the other side, just like an inverted umbrella, right? So let me explain the backside attack, and then we can go into a little bit more detail, right? So let's just say that we have this particular compound with a leaving group, and a general leaving group, and a nucleophile, right? So let me highlight this in red again. A backside attack means it's coming from this direction. That leaving group is leaving. Okay, so now what we have is an inversion of stereochemistry, kind of like the nitrogen barrier to inversion. We have an inversion at this stereocenter as well. Again, comparing it to an umbrella flipping inside out. Okay, so this would be our transition state. So we have partial bond formation as well as bond breaking. And once that leaving group leaves, that carbon center is kind of flipped, and now the wedge and the dash are not on the left side, they're on the right side. Okay. Now that's because at this in this particular transition state, that carbon is actually planar, and then the nucleophile and the leaving group are 180 degrees apart. And this actually makes perfect sense in terms of an electronic argument, because the nucleophile is negatively charged. That leaving group after it leaves is negatively charged. And so in terms of like electron repulsion, you want those to be as far away from one another as possible to reduce the energy of the whole system or the mechanism. So remember, negative or like charges repel one another, and so when that nucleophile comes in from the back, it's actually approaching in the lowest energy possible, lowest energy mechanism possible, because there's no repulsion between that nucleophile and the leaving group. And this is kind of supporting the idea that an Sn2 reaction would be a backside attack. And this, I mentioned further studies were needed. Through those further studies, it was seen that reaction after reaction resulted in an inversion of stereochemistry. Okay, so let's do a couple examples just to show you a quick way to obtain the answer for an Sn2 mechanism and the stereochemistry that we would see in the end. So basically what I mean is we have this particular alkyl bromide, we have this cyanide, that's is our nucleophile, and then the bromide is the leaving group. And now I want you to draw, assuming this is an Sn2 mechanism, draw the products. Okay, so nucleophile attacks from the backside. Okay, and then that means that we have an inversion of stereochemistry for our products, right? So inversion for Sn2 mechanism. Now, the quick and easy way to draw that inversion is, first of all, everything is left the same, and we only focus on the carbon of interest, the carbon with the leaving group. And then we can just draw the opposite kind of, not sign, but opposite configuration that the leaving group was. So the leaving group was a wedge. Now we draw the nucleophile on there with a dash. And that's a quick and easy way to draw that inversion product for Sn2 mechanisms. It's not always necessarily going to be that easy, but let's say we have this particular alkyl bromide, and then we have this ethoxide. Okay, this is our nucleophile. That is an electron-rich species. We have our leaving group here in the bromide, and we have a backside attack of that nucleophile, right? So we're approaching from this side, and that forces that bromide to leave. And then we need to draw our inversion product. So there's a couple different ways you can do it from the way that this particular compound is drawn. Now I'll show you. The first way is basically just drawing the mirror image. So imagine you were drawing, trying to draw the enantiomer for this particular alkyl bromide, okay? So what you would do is draw the mirror image of it at first, okay? But what I'm going to do is kind of leave out the bromide, okay? Draw everything else, and then substitute that bromide with the nucleophile, which is the ethoxide, okay? So that would be the inversion product because it's the mirror image of it, okay? Now another approach would be to draw the same orientation for the bonds that are in the plane of the board, like the hydrogen and then that bromine, but you leave and substitute the bromine for the nucleophile, and then the wedges and the dashes, all you have to do is just swap those groups. So the deuterium, the D, is on the wedge, and now the dash is the ethyl group, okay? So now this is definitely going to take some practice, so I encourage you, obviously, to do the homework multiple times. Now, it seems easy enough, right? We've got these, we have inversion about that stereochemistry for these alkyl halides, but these two examples were primary and secondary alkyl halides, right? Now, of course, it's OChem, so we got to make it more complicated. It's not as straightforward as it might seem at first. So, but we have to look at the identity of the R group because it does matter in the type of reactions that occur. So this, we've been talking about the Sn2 reactions, right? But sterics is actually going to play a huge role in this. Okay, so Sterics will either allow this reaction to occur or prevent it from happening and then undergoing a different mechanism. So let's say we have a methyl group with a leaving group, or we have this these other alkyl groups with leaving groups on them. We can classify them as basically a methyl, a primary, secondary, or tertiary alkyl group with the leaving group. So typically we'll see alkyl halides for Sn2 reactions, but we could see other good leaving groups. So, sorry, let me just struggle real quick to draw this arrow. What I'm trying to do is draw this arrow from right to left. So as we go from tertiary to primary or methyl, we have an increased rate of an Sn2 reaction, okay? And this is strictly because of steric hindrance, okay? So methyl and primary groups, those are super fast Sn2 reactions because there's only hydrogens really there that are kind of like budding on the nucleophile that's coming in, where that secondary one has got a little bit more stuff going on around it, right? So that's much slower. And then that tertiary just doesn't happen at all. That's too sterically hindered for this reaction to move forward via an Sn2 mechanism. As we see, we do have another way to make this particular substitution occur. Okay, so just to summarize, the Sn2 reaction, for now though, because we're going to introduce a couple other fun things, right? Like I said, it seems pretty straightforward. We're probably not done explaining it. So we have a few factors, right? So we've got the kinetics, the mechanism, stereochemistry, identity of R. Let me just draw this terrible table real quick. That crooked lines are bothering me, I'm sorry. Kinetics, we have second order with the rate is equal to the K times the concentration of the alkyl group as well as the nucleophile. The mechanism is one step, and the stereochemistry is as a result of backside attack, we get inversion of stereochemistry. Okay, and then the identity of R, basically, if we have an unhindered R group, that's going to be a much faster reaction, okay? So it reacts fastest. All right, so that's it for now, and kind of the introduction of nucleophilic substitution with the bimolecular mechanism. Now what we want to do is introduce something called Sn1, which we already said was substitution nucleophilic unimolecular. Okay, so that's going to be a two-step process, so check out that next video for that. Okay, all right.